Okay, topics for this week are vector spaces, subspaces, which are just smaller vector spaces, and column space.
You're not gonna do the null space?
I think so. A lot of people haven't gotten there, I don't
Oh, that sucks, man.
think. Don't worry, we'll get there. Okay, so a vector space is just a collection of vectors, a set of vectors with two operations. Vector addition and scalar multiplication. Scalar multiplication so here I'm using the word vector in a kind of abstract way. A vector is anything that you can add to other vectors and multiply by numbers. So a vector could be like an ordered pair, like we've been talking about, or it could be a function. Like x squared, that's a vector, or it could be a matrix. A vector could be a matrix.
Which
These
is
are all-
just, the matrix is just a set of vectors, correct?
Yeah, a matrix is essentially another ordered pair like this one. So a matrices, functions, those are all examples of vectors. Polynomials, which are also functions.
Oh, yeah, he covered polynomials as well.
Those are all vectors. So using that word in a kind of abstract way. So some examples of vector spaces. We're familiar with R2, the set of ordered pairs x, y, where x and y are real numbers. You know, the whole Cartesian plane, that's a vector space. With the vector addition is just regular addition of vectors. And then the scalar multiplication is the usual multiplication of a number times a vector.
What's the difference between R2, R3, R? Because like they'll say, it was the element of R, it's the element of R2, it's the element of R3. What's the difference? Is it just a different dimension?
Yeah, it's basically a different dimension. So R3 is just order triples. So you now have just another dimension in there. So three-dimensional space now. Another example of a vector space is M2R, which is the set of all 2 by 2 matrices. Which is this set A, B, C, D, where A, B, C, and D are real numbers. So that's a vector space. With vector addition, which is just the usual addition of matrices, component-wise. B plus F, C plus G, D plus H. And then scalar multiplication. You know, you just take a number and you multiply each entry by that number. That's the scalar multiplication here. Here the vectors are matrices. More generally, M in R, which is a set of n by n matrices, that's a vector space. And Rn, which is the n-dimensional set of vectors, I'll just say this is a vector space. Another example of a vector space would be, you could call it P2. It's a set of all degree 2 or lower polynomials. So that's the set of polynomials that look like this: ax squared plus bx plus c, where a, b, and c are real numbers. So a vector in this space is like 2x plus 1, or x squared plus 3x plus 5. Those are vectors in this space. And the vector addition is just the way you would usually add polynomials. Ax squared plus bx plus c is this polynomial plus this other one, dx squared plus ex plus f. That gives you a plus d x squared plus b plus ex plus c plus f. That's the vector addition. And then you can imagine scalar multiplication just takes a number and multiplies it by each coefficient, distributing across like usual. So in general, Pn is a vector space. Degree n or lower polynomials. That's a vector space. So vector spaces are pretty simple. We've already dealt with them a lot. We just didn't call them vector spaces. Okay, we need to talk about smaller vector spaces inside bigger vector spaces, which are just subspaces. A subspace is a subset of a vector space, which is itself a vector space. So you have some subset of this vector space. This is just a smaller vector space. So like the picture, nice picture would be, that's V, smaller vector space, that's S. So there's two conditions that you need to check if you're trying to show that something is a subspace of another vector space. So if you have a subset S of a vector space, then it's a subspace if two conditions are satisfied. If V and W are in S, then V plus W is also in S. So that means that It's closed under vector addition. Closed under addition. And secondly, if V is you have some vector V in the space S, in the set S, then C times V is also in S for any number C. So that's closure under, it's closed under scalar multiplication. So those are the two conditions. Just check if something is a subspace. It needs to be closed under addition and scalar multiplication.
When you say V plus W is the element of S, it's original S?
Yeah, the subset. That S. If you take two guys inside S, their sum also needs to be in S. So, for example, if your big vector space is R2 and your subset is the line y equals x, which as a set is the set of ordered pairs x, y, where the y coordinate is the same as the x coordinate. So this guy is S. So this is a subspace. Let's check that by checking that it's closed under addition and multiplication. So first of all, let's say V and W are in S. So when I say that V and W are in S, I mean that V is a vector x1, y1, and W is a vector x2, y2, where y1 is equal to x1 and y2 is equal to x2. That's what it means for V and W to be in S. So we'll check V plus W. V plus W, we add these two vectors together, we get x1 plus x2 and y1 plus y2 for the components. But we know that y1 is x1 and y2 is x2. So if we use that condition here, then that means this is equal to x1 plus x2, comma, x1 plus x2. So the y coordinate is the same as the x coordinate, meaning v plus w is also in S. So that's vector addition satisfied. I'll say V is in S and C is any real number. C is a real number. So V is x1, y1, where y1 is the same as x1. So C times V is C times this vector. So if you move the scalar inside, you get cx1, cy1. But if we apply this condition that y1 is equal to x1, then that means that this is cx1, cx1. So the y coordinate is still the same as the x coordinate again. So this means that CV is in S. So these are the two conditions we need to satisfy. So it's a subspace. Now we could change this example just slightly. Let's say V is R2, and the subset is the line y equals x plus 1, which is the set of pairs x, y plus 1, or x plus 1. So this is y equals x plus 1, that's S. So S is not a subspace. Let's check why that is. If we take two vectors in S, this means that y1 is x1 plus 1 and y2 is x2 plus 1. If we add these two vectors together, v plus w, it's x1 plus x2, comma, y1 plus y2. But if you use this condition right here, then you get x1 plus x2, x1 plus x2, or x1 plus 1 plus x2 plus 1. But that's x1 plus x2 plus 2, not x1 plus x2 plus 1. So it has the wrong form. This is not an element in S. This is not in S, because it's plus 2 instead of plus 1. So visually, we have our line here. I have some like for example, you could take 0, 1, that's in S, and 1, 2, that's in S. So I have this vector 0, 1, and I have this vector 1, 2. But when I add them together, if you add these two vectors together, you would get that vector, which is not on the line. So if you add these together, you get 1, 3, which is not on S. Another way to check it would be via scalar multiplication. So if I have any vector in S, I need to be able to multiply by any scalar I want and have it still be in S. So I need to be able to multiply by 0, by the number 0, and have that vector still be in S. So I need to be able to take 0 and multiply it by x1, y1, which is just 0, 0. But 0, 0 is not in S, because it doesn't pass through the origin. So it's not closed under scalar multiplication either. So this multiplication by 0 thing is usually a pretty good way to check something is not a subspace. So that's a fact. Every subspace contains the 0 vector, passes through the origin. Because you need to be able to multiply by 0 and be closed under scalar multiplication when you do that. So if you don't pass through the origin, not a subspace. So with that fact, we can conclude quickly determine that some other things are not subspaces, like y equals 3x plus 7, not a subspace of R2, because it doesn't pass through the origin. Y equals x squared plus 1, not a subspace, because it doesn't pass through the origin. So that's a good way to check if something is not a subspace. But there are things that do contain 0 and are still not subspaces, right? So that's not sufficient. You do have to check both vector addition and scalar multiplication completely. So another example would be, say V is M2R, the set of all 2x2 matrices. And let S be the set of 2x2 symmetric matrices. So this is a subset, but is it a subspace? So this is a set of matrices A and M2R that are equal to its transpose. A is A transpose. That's what it needs to be symmetric. So we can check vector addition and scalar multiplication. So if A and B are two symmetric matrices, then we want to know, is A plus B transpose equal to A plus B? That's what we need to check. Well, A plus B transpose is A transpose plus B transpose. And since A and B are both symmetric, since they're in S, A transpose is equal to A and B transpose is equal to B, so this is equal to A plus B. Because this is equal to A and this is equal to B. So it's closed under vector addition. Does that make sense? Scalar multiplication. Say A is in S and C is a real number. We need to check, is C A transpose equal to CA? Well, that one's probably even easier because CA transpose is just C times A transpose. And A transpose is A, so this is CA. So it's closed under addition, scalar multiplication. So the set of 2x2 symmetric matrices is a subspace of the set of 2x2 matrices. So S is a subspace. Another example would be if V is the same M2R, S is the set of 2x2 upper triangular matrices. I think S is a subspace. If you add two upper triangular matrices, is it still upper triangular? So this is a set of matrices of the form A, B, 0, C, where A, B, C are real numbers. So if you take two upper triangular matrices, you add them together, it's still going to be upper triangular, because you'll still have a 0 here. And if you multiply it by any number, it'll still be upper triangular, so S is also a subspace. Space of V. You could also do lower triangular matrices. What about S is the set of invertible 2x2 matrices? Set of matrices A such that A inverse exists. So what about this one? Think that's a subspace?
I'm just copying. I'm not really following. It's just going really quickly.
Two by two invertible matrices. If you add two invertible matrices, is it still invertible?
It should be.
No,
I think so.
no, can't take that.
You don't think so?
Yeah, so for example, if you add the 1 0 0 1
Uh-huh.
negative 1 0 0 negative 1
Right.
add together.
Yes. That's a good example. So you said if you take A equals 1 0 0 1, that's invertible, so it's in S. If you take B equals negative 1 0 0 negative 1, that's in S. It's also invertible. But if you add these two together, you get 0 0 0 0 0, which is not invertible. So it's not closed under vector addition. Also, it doesn't contain the zero vector. It doesn't contain the zero matrix. Because 0 is not invertible. So, in this case, S, the space of the set of 2 by 2 invertible matrices, is not a subspace. Okay, so I want to talk about the set of all linear combinations of some vectors and how that can give us some subspaces. So say V is any vector space. It could be a set of vectors in Rn or matrices or something. The set of all linear combinations of two vectors, u and v, inside V, is the set S equals Cu plus dV, where C and D are real numbers. So we've talked about linear combinations a lot. So this is just the set of all linear combinations for any numbers C and D. So a fact is S is a subspace. So the set of all linear combinations of two vectors is always a subspace of V in this case. V is any vector space. And it's kind of just because of the definition of the set of all linear combinations, because the sum of two vectors is still a linear combination. And if you multiply a vector by a number, that's still a linear combination. So it's closed under addition and scalar multiplication by definition. Similarly, you could define the set of all linear combinations of three vectors, u, v, and w. CU plus DV plus EW, where, oops, this should be a plus, where C, D, and E are real numbers. So same thing, just with 3 vectors now, that's still a subspace. For the same reason. So in general, the set of all linear combinations of any set of vectors is always a subspace. So there's a name for that set of all linear combinations. So in general, set of all linear combinations of some vectors v1, v2 through vn is called the span of these vectors. So the span of vectors is always a subspace. In some sense, it's the smallest possible vector space containing all of those vectors in the set. So for example, the span of, so if V is just R2, then the span of these 2 vectors, 1, 0, and 0, 1, that's all of R2. So it's definitely a subspace. Or if you just take the span of 1, 1, 2, 2. So these are linear combination of each other. So that's 1, 1, but 2, 2 is just same vector, just slightly longer. So this is just the same thing as the span of 1, 1, which is the line y equals x in R2. So the span could be 2-dimensional or 1-dimensional object. So we talked about lines as subspaces, but also you could do planes. So the plane x plus y plus z equals 0 is a subspace of R2, or sorry, R3. But the plane x plus y plus z equals 1 is not a subspace. Because it doesn't contain the 0 vector, because 0 plus 0 plus 0 is not equal to 1. So this plane doesn't pass through the origin. So that one's not a subspace. So let me summarize that couple of facts. So any line through the origin is a subspace. any plane through the origin is a subspace. And does set containing 0, the 0 vector, that's a subspace on its own. Just 0, that's a valid subspace. Okay, column space. You guys talk about column space of a matrix. Column space. Column space of a matrix. Column space.
It's just the space where the pivots are.
Yeah, it's the set of all, it's basically the span of the columns of a matrix. So given any matrix, A, could be a square matrix, could be not square, it could be 2 by 2, 3 by 3, anything, any matrix A, the column space of A is the span of the columns of A. So the set of all linear combinations. So if A is the matrix whose columns are A1, A2, A3, then the column space of A, denoted C of A, is the span of A1, A2, A3, which is the set of all linear combinations. So CA1 plus DA2 plus EA3, where C, D, and E are real numbers.
And A1, A2, A3 are, what is that? Is that the columns?
Yeah, they're supposed to be the columns of A. So the column space of the identity matrix, 2 by 2 identity matrix, is all of R2. In general, for the n by n identity matrix, the column space is all of Rn. If A is the matrix 1, 2, 3, 4, the column space is the span of 1, 2, and 3, 4, which is just any linear combination of these two vectors. But these are two like independent vectors. They're not parallel. So you can write any vector as a combination of these two in R2. So since any vector in R2 can be written as a combination of these, the span of these two vectors is also all of R2. So there's a lot of different matrices whose column space gives you all of R2. But for example, if A is like what I kind of did earlier, 1, 1, 2, 2, the column space of A is the span of these two vectors. But 2, 2 is already a linear combination of 1, 1, so this is just the span of 1, 1 by itself, which is not all of R2. It's just a line y equals x again. Column space of A is that line. So in this case, this matrix had linearly dependent columns. So the linearly dependent columns of a matrix don't contribute anything to the column space. So the column space is the span of all the columns, but it's also equal to just the span of only the linearly independent columns. So the dependent vectors are kind of superfluous when you think about the column space.
So then the column space will always be the span of something.
The span of the columns of the matrix. So take this matrix B equals 1, 1, 0, 2, 1, 3. So in this case, the column space is the span of these three vectors. But 1, 3 is just 1, 1 plus 0, 2. So this is the same as just the span of the first two vectors. And that's all of R2. So even if you have more than two columns, that's not necessarily going to give you more than just the two-dimensional space for this matrix. So take this matrix 1, 1, 2, 0, 3, 3. Column space of this matrix. Oh, I should have put B here, right? Column space of B is the span of these two columns. Which is the set of all linear combinations of these two vectors, which will give you a plane in three-dimensional space. So you can imagine if I took some vector which is linearly dependent upon these two columns, and I put it as a third column in this matrix, the column space wouldn't be changed at all by that. It would still be this same plane in R3. Okay, so there's some important things about the column space in relation to solving systems of equations, solving AX equals B. So say you have a matrix. 1, 2, 3, 4. Negative 1, 2. And x is negative 1, 2. So the product A times x, matrix times vector, can be written as negative 1 times the first column of A plus 2 times the second column. So A times x is a linear combination of the columns of A. So there's another way you can think about the column space. The column space of A, which is the set of all linear combinations of the columns of A, is just the set of A times x. where x is a vector in R2. Because any linear combination of columns of A is just represented as A times X. So if I have a system of equations Ax equals B, then I'm saying the vector B is in the column space of A. So Ax equals B is solvable if and only if B is in the column space of A. So that's the important connection between column space and solving Ax equals B. You can solve it if and only if that right-hand side vector is in the column space of A. So an example, so take this matrix 1, 0, 0, 0. The column space of A is just the x-axis, because it's just the span of 1, 0. 0, 0 doesn't add anything to the span, so that's just the x-axis in R2. So if you take the vector B, which is 0, 2, that's not on the x-axis, so it's not in the column space. That means that Ax equals B is not solvable for any x. You can't find a solution to that, which makes sense, right? We've already done those kinds of problems. Because if you multiply this out, on the bottom you have 0 equals 2. So no solution. So that aligns with what we've already learned. If you consider the matrix, the 3 by 2 matrix I wrote down earlier, if you take this vector B, which is like 2 times the first column minus 1 times the second column, this is 2, negative 1, 1. That is an element of the column space, because it's a linear combination of those two columns of A. So that means B being in the column space means that Ax equals B is solvable. So well, obviously it is, because the solution is 2, negative 1. Right, because I took 2 of the first column minus 1 of the second column, so the solution is 2, negative 1. Okay, any questions about column space, vector spaces, subspaces?
For this example, this
Yes.
B equals 2 times the column space of 1, 1, 2. What is that mark underneath the 2 and the mark underneath the?
I was just writing things.
Is that supposed to be a -1?
Yeah, this is a -1. This one.
Why is it a negative? You're just, what are you,
I was just
you was just subtracting?
yeah, I was just taking some random linear combination.
Okay.
I was just kind of give an example of how something that's in the column space. If you have a vector that's in the column space, then you can solve this system AX equals B.
Gotcha. Do we have to define that 2 and -1? Well, obviously they're all elements of the system.
Well, so if I change this matrix a little bit by just adding on another column, if I take A and I give you another column, well, let's say the other column is 2, -1, 1, which was
Wait.
the vector B. Yes.
Going back, how is B an element of the column space when B is 2, -1, 1, and
Yeah.
2, -1, 1 is not in A?
Right, B is not a column of A, but I explicitly defined B as a linear combination of the columns of A. So B is 2 times the first column minus the second column, meaning B is a linear combination of the columns. So B is definitely in the column space.
Gotcha. So if B is any linear combination, whether it's scalar or anything like that, gotcha.
So if I take this matrix A and I adjoin this new column to -1, 1, which was the vector B, that was already in the column space, so it doesn't really change the column space at all. Let me call this matrix D. The column space of D is going to be the same as the column space of A. But now, the solution to AX equals B is not unique. If I use the same vector B as before, the solution to dx equals B is not unique. It was unique before. X had to be 2, -1. This was the only solution before. But now the solution to dx equals B is not unique. Because, for example, D times 2, -1, 0 still gives you B. Because 2 times the first column minus 1 times the second column gave us B. So same thing here, that'll give you B. But also D times 0, 0, 1 gives you B. So there's 2 solutions now to dx equals B. So that's kind of interesting. You don't change the column space at all by adding some new columns, but now it affects whether or not your solution is unique. Okay, I think I pretty much killed that topic.
Nailed it.
Nailed it. Next week, probably null space, basis for a vector space, dimension. Good stuff.